It's too amazing that 3% of worldwide carbon emissions are attributed to shipping. Biofuels, green and blue hydrogen, and ammonia have all been proposed as replacements to fossil fuels for use in ships in order to meet global net zero targets by 2050. But what if we could go back to the beginnings of shipping, when sails were powered by the wind, but with today's and tomorrow's technology? In today's video, we will look at wind-powered ships and how it will change the future of shipping. You may also have the question, could wind decarbonize shipping more quickly than other options, like biofuels and hydrogen? Let's find out. Several sectors throughout the world have been creating, enhancing, and transitioning to green technology in order to achieve carbon neutrality in the coming decades. One of the most difficult is the shipping industry, which emits 940 million tons of CO2 each year, accounting for around 2.5% of global carbon emissions. Given how reliant transportation is on heavy fuel oil and the fact that container ships transport over 80% of global trade today, this shouldn't come as a surprise. And pandemic-related container ship backlogs in ports around the world aren't helping. On any given day, around 5,000 container ships traverse the seas, with heavy fuel oil powering roughly 90% of them. Every year, a high ship can emit over 5,000 tons of sulfur dioxide pollution, which is dangerous to the environment and people. Welcome to Future. Don't forget to like this video and subscribe to our channel for everything on future technology. But how did we get here? Shipping and boats have been around since 4000 BC in Egypt. The Nile River was crucial to Egyptian communities' existence and was heavily used for transportation. The most astonishing reality, which I am telling you, is that Spain and Portugal began to construct carracks, enormous sailing ships used for excursions, in the 15th century. From 1519 to 1522, a carrack was the first ship to sail around the world. Ship advances continued throughout the 19th century, when the clippers, a bigger but faster ship design, appeared. T-clippers were used to transport. You probably figured it out. In favorable wind conditions, it could reach a top speed of 20 knots. That's faster than today's cargo ships just for fun. Many sectors, including shipping, benefited from the Industrial Revolution. Steamships grew popular, but they weren't a practical choice for cargo transport because the fuel and engine took up too much room. Oil became popular in the 1950s, allowing fuel tanks to be smaller and cargo space to expand. Since then, the use of this inexpensive but dirty fuel has caused an increase in environmental difficulties associated with shipping, and cleaning it up hasn't been easy. When we zoom out to now, we can see several heavy fuel oil replacements that have emerged to make ships more environmentally friendly. Hydrogen, ammonia, and biofuels are examples of such substances. Is this, however, the answer? What about combining all the technology and know-how available today with some good old wind recall? Clipper ships were really faster than today's cargo ships. We normally picture three-bladed turbines dotting the horizon or massive sails on ships when we think of wind power. However, as I discussed in my video on solid-state wind energy, there are a variety of other options today, and shipping is no exception. Rotor sails were the first wind-powered ship technology to be considered. Fletcher rotors are vertical rotating cylinders designed by Finnish engineer Sigurd Savonis at the turn of the 20th century. However, they were named after Anton Flettner, a German aviation engineer who successfully sailed a rotor ship prototype in 1926. The Magnus effect is used to collect wind energy in rotor sails. When the wind drives the revolving cylindrical rotor perpendicularly, it creates a force at a right angle to the flow stream, according to this fluid dynamics principle. The spinning of the cylinder speeds up one side while slowing down the other when the wind blows laterally over the ship's deck perpendicular to the ship's direction of travel. This generates forward thrust or lift, which propels the ship forward. There are three factors to keep in mind in order to succeed. 1. Drag is in the force acting in the opposite direction of movement. 2. Lift is the force acting at a right angle to the direction of drag. And 3. Thrust is the force required to overcome the drag and generate the lift force. Wing sail technology, like rotor sails, requires careful consideration of various elements such as wind speed, and ship type, as well as highly planning and wind study. This method is particularly efficient when sailing upwind because no electricity is required to provide lift. This technology has the advantage of being able to operate the wing sails at a tiny angle to the apparent wind, which is the wind you feel on you as you sail, allowing these sails to harness the wind almost all of the time. These airfoils, like rotor sails, eat up cargo space. While Flettner rotors must be laid down as the ship passes beneath a bridge, other airfoil technologies can be retracted. Several businesses are attempting to commercialize similar technologies, including London-based Amonia, which uses rotor sail technology. They use lightweight composite materials for the rotor and steel for the tower. Their system weighs less than 0.1% of the ship's deadweight when these components are used. The rotors on the Amonia can be folded or repositioned on the deck to avoid interfering with cargo operations. Amonia predicts that for capsized bulk give carrying 180,000 dWt, 21.9% fuel and pollution reduction can be realized when sailing a voyage from San Francisco to Shanghai and back. Every year, 1,413 tons of fuel may be saved for just this one ship. A 64,000 dWt geared Ultramax bulk carrier with 4 rotor sails was one of the company's projects completed in 2018. It's worth mentioning that the equipment installation took less than 2 hours each unit. The ship cruised for 518 days, covering 174,000 nautical miles and visiting 50 ports till last year. Overall, the estimated fuel and carbon emission savings are 12.5%, 73 tons of gasoline. A case study for a carrier delivering coal, iron, ore, and grain traveling from Egypt to France with 4 Norse Power Flettner rotors costing around $750,000 per rotor was published in the Environmental Science and Pollution Research Journal. According to the analysis, annual fuel savings totaled 1,693 tons. Annual fuel savings might exceed $1.3 million by the conclusion of the project's lifespan. The payback period varied between 6 and 8 years, with an LCOE of $0.05 per kWh after 8 years, depending on fuel costs. Moving on to wing sails, this technology is still in its infancy, but Oceanbird is working to bring it to market. It's difficult to believe that the wing sails will reduce carbon emissions by 90%. For the time being, they've constructed a 7-meter scale ship to gather data and improve functioning. The business plans to ship its first vessel in 2024, so it's still a long way off. Bar Technologies, based in the United Kingdom, is working on shipping wing sails. They've inked a deal with Cargill, the agriculture behemoth, and hope to get the first ships on the sea by 2022-2021. While hybrid wind systems appear to be promising, many are still in the pilot stage, so we can't rely on them as our only option. Alternative fuels like ammonia and biofuels are another topic that is attracting a lot of funding and interest. Methanol has been investigated, however, it is only environmentally friendly if it is produced using biomass gasification or renewable electricity with carbon dioxide absorbed. Unfortunately, the majority of today's methanol is made from fossil fuels. Ammonia, which is currently produced from natural gas, falls into the same category. Green ammonia, on the other hand, may be generated using renewable energy and hydrogen from water electrolysis. There may be a way to produce cleaner fuel there. For example, Maersk invested $1.4 billion on carbon-neutral methanol-powered ship. The ships will transport approximately 16,000 cargo. As part of this plan, European Energy and its Danish subsidiary Reintegrate would produce 10,000 metric tons of green e-methanol annually for use in ships. Ammonia, a newer option, is similarly in its early phases of development. Hyundai Heavy Industries of South Korea, for example, has received preliminary approval for a 227-meter-long ammonia-fueled vessel that will transport ammonia. Another company, Wärtsilä, is betting on hydrogen and ammonia as a shipping fuel. By 2025, the business hopes to have a pure hydrogen engine and plant design available, as well as an ammonia-based engine this year. Despite development in green shipping technologies, the industry's low-carbon future is still increasing slowly. Wind power technologies, particularly wing sails, are still in their infancy. Thus, additional testing and design modifications are required to confirm the technology's long-term viability. However, the findings for rotor sails are promising. Ammonia fuel cells and green methanol engines, meanwhile, are still in the development stage for ships, with testing scheduled in the coming years. We have a long way to go, but progress is being made, so it will be very helpful in wind-powered ships in the future of shipping. What are your thoughts on wind-powered shipping? And do you think it will change the future of shipping? Let us know in the comment below. Don't forget to subscribe to our channel to stay updated on anything on future technology. Thank you for watching.